Hello, 7th graders. We're in section 5.3, and we're going to take what you learned last year in your knowledge about graphing and extend it to function rules, tables, and graphs. Now, you can take a function and you can model it. A function can be modeled using rules, tables, and graphs. A function rule shows how the variables are related. A table identifies specific input and output values of the function, and a graph gives a visual piece of the function. Now, everything I just said can be found on page 263. You don't need to write it down, but I'm going to take a moment in one problem and kind of explain each of these things I just talked about. So, when I say a function rule is something that looks like this. Y equals negative 1/2 x plus 1. Now, that's an equation. And I know you've represented it as an equation before, but it's also called a function rule. I could also write it as the function notation. F of x equals negative 1/2 x plus 1. Either way, they're the exact same thing. Now, if I wanted you to model this function using table of values and a graph, a table of values is what you've used before called a t-table. Now, there are numerous ways to write a t-table. Sometimes you just see x and y, sometimes you can show your work, and a table of values are any values of x that you want to plug in. Now, if you remember, x is what you plug in, which is your input, which is your domain. Y is your output. So if I plugged in here -4, 2, and 0, I'm just making these three numbers up. You can use anything you'd like. If you plug that in, negative 1/2 times -4 gives you positive 2, and 2 plus 1 gives you 3. Now, if you plugged in 2, negative 1/2 times 2 is negative 1 plus 1, which gives you 0. And then if you plugged in 0, you would get negative 1/2 times 0 plus 1, which would give you 1. So as ordered pairs, these would be -4, 3, 0, 1, and 2, 0. Now, as a graph, we are going to draw an x and y axes. Now, in your notes, you can make a rough graph like I am doing now, but on homework, you'll have to use graph paper. When you draw any graph, make sure you label the x and y axis, as well as putting arrows on all sides. So if we graph this, our x has to go to -4. Make sure you also number them so I know what you're counting by. And then we graph them. -4, 3, 2, 0, and 0, 1. Now when you graph your line, you're going to go through the points and put arrows on both sides. And that is graphing using a t-table. You've done that before. We're just calling them different things, like a function rule and a table of values using f of x. Now we're going to be doing a lot of real-life situations. Make sure that if you draw a graph of real-world situations, you use appropriate intervals for the units. Also make sure the intervals are equal. Also, if the data are positive, use only the first quadrant. So let's do an example of this. Example number 1 is found on page 264. It says that your group is recording a CD. You want to copy and sell it. One company charges $250 for making a master CD and designing the art for the cover. There is a cost of $3 to burn each CD. The total cost, P of C, depends on the number of CDs C burned. Write a function rule to make a table of values and a graph. So let's first write our function rule. Now, in this case, notice that it says the total cost is P of C. Therefore, instead of Y, we're going to use the letters P of C. So we're going to start off our function as P of C. That means the total cost is based on C, which is the number of CDs. So what do we have to spend? Well, they charge $250 plus $3 for each CD. Now, if we make a function table, we are now not going to use x and y. We're going to be making X, which is C, that's the number of CDs. That value is what you plug in, the number of CDs. What comes out is the total cost, which is P of C. Now in this case, we could start at 0 if you wanted to. But then let's work our way up. Like let's use, instead of 0, 1, and 2, think about how many CDs we would have to create. So you could, for example, use 100, 200, and 300. You don't have to use those. You could use 50, 100, 150, and so on. So if we plug them in, now I would assume you can do that in your head. 3 times 0 plus 250, that's going to give me 250 bucks. Plug in 100, that's going to give you 550. You plug in 200, that's going to give me 850. If you plug in 300, you're going to get 1150. Now we're going to create our graph. Since all we're talking about are positive numbers, we only need the first quadrant. So we need to label our axes, C and P of C. Now at the bottom, we're going to label. So we're going to label the bottom number of CDs and the side recording cost, which is in dollars. Now we number. Whoops. If we number, we start with 0, and we can count by 100s, 200s, 300s. You can count by whatever you want. So let's count by a 100, 200, 300, 400. So our biggest value we have to graph is 1150. So I'm going to go up to 1200. So I'm going to count my other graph by 300s. So 300, 600, 900, 1200. So I have each axis as different intervals, which is fine. Now I graph 0, 250, 100, 550, 200, 850, and 300, 1150. Now obviously it would be much better, and we should use a graph or graph paper. Now I'm going to connect and make a line. Why would I not have an arrow going to the left? Because you don't have negative number of CDs. So we can't go to the left. The next thing we're going to talk about is how we use our data. This is important. Continuous data are data where numbers between any two data values have meaning. Use a solid line. Here's what this means. Some graphs involving real-world situations are going to involve lines where you connect the dots. Some data points, we're not going to connect the dots, and that's what's called discrete data. Discrete data are data that involve a count of items, such as the number of people or the number of cars. For example, if I am talking about how many people are going to the movies on a Friday night, and you want to make a graph, you are not going to connect the dots, because if you connect the dots, you are meaning that anything on that line is a solution, which means decimals and everything else. Well, you can't have 5.7 people at the movies. So you are going to represent that only with dots and not by connecting the points to make a line. Now, in some cases, like the example we just did, the scale of a graph makes it impractical to use a dot for each value in the domain. So a solid line is used. Be aware of the real-world situation to determine if data graphed should be continuous or discrete. So let's do an example of that. Now in example 2, you do not have to copy any of this down. You can make notes for yourself, or you can write things down. But my whole goal is not to show you how to graph it. My goal is to show you why it's discrete or why it's continuous. So in this example, I want you to determine whether the function rule models discrete or continuous data. So I've already drawn the graphs for you, but let's look at it. A photography question. An automatic photo booth charges $3 for a sheet of photos. The function C of P equals 3P describes the cost of P sheets. So as you can see here, here's a table. We plug in, well, one sheet is going to cost $3. 2 sheets is going to cost $6. 3 sheets is going to cost $9, and so on. Notice that if you have 0 sheets, you'd have 0, but 1 sheet costs $3, 2 sheets cost $6, and so on. You cannot buy part of a sheet in a photo booth. So the data are discrete. That's why we do not connect lines. You cannot go to a photo booth and buy 4.2 sheets of photos. You only can buy whole numbers worth of photos. Therefore, a line is not going to represent your solutions. Points are. Now, if we're looking at part B for physics, the function m of w equals 1/6 w describes your weight on the moon as a function of your weight on the earth. So your w, which is the weight on earth, we divide that by 6. So we take 1/6 of the weight to give you the weight on the moon. So if you're 60 pounds on earth, 60 divided by 6 is 10 pounds on the moon. 90 pounds on earth, 15 pounds on the moon, and so on. If we graph them, you can see we have all these data points. And the other thing I want to show you is that you can show a break. This is also important. Notice right here, our first value that we plugged in was 60. You can actually do a break, which is almost like a little heartbeat right here. It looks like this. Let me draw it. That's what a break is. A break is only used at the beginning of values on an axis where you skip a whole bunch. So we can skip a bunch and then start at 60 and then we increase by 30 each time. So if you don't want to put 0 and then 30, 60, 90 and so on, you can do a break. All right, so as you see here, 60 weighs 10, 90 weighs 15 and so on. Your weight can be measured in parts of a pound. You don't have to be exactly 60 pounds. You can be 60 and a half, 61 pounds. That's why the data is continuous. Therefore, we connect the points with a solid line. Now, in the next example, you're going to realize that some functions are not straight lines. You can graph a function as long as you know its rule, which is, remember what a rule is just your equation. After you have graphed the ordered pairs that you have calculated from the rule, join the points with a smooth line or a curve. So we're going to graph some of these, and this might be the first time you've ever graphed some of these lines or some of these functions. So in A, we're going to graph the function y equals the absolute value of x plus 1. The first thing we're going to do is make a t-table. Now I'm going to show you the other way that if you would like to make a t-table, you can. In here in the middle, I'm going to write what the rule is, and you can do this if you want. And then I'm going to pick any values you want of x, your input. Now when you have other things other than lines, I would pick some negative and positive values. So here, I'm just going to pick, let's say -2, -1, 0, 1, and 2. You can pick whatever you'd like. If you want to show this middle part of your table, you can actually show your work here. So you could put the absolute value of -2 plus 1. Then the absolute value of -1 plus 1. The absolute value of 0 plus 1. The absolute value of 1 plus 1. The absolute value of 2 plus 1. If you want to do that, you can do that. And then if we solve that, this would give you the absolute value of -2, which is 2, plus 1, that would give you 3. This would give you 2, this would give you 1, this would give you 2, and this would give you 3. So if we graph this, now I'm going to cheat and have my magic graph appear. If you graph this, you would graph the points -2, 3, -1, 2, 0, 1, 1, 2, 2, 3. This may be the first time you've ever done an absolute value function. An absolute value function, if you want to make note of this, an absolute value function is always going to look like a V, and it's going to come to a point. So that's what it's going to look like. In part B, we're going to graph another function. The function f of x equals x squared plus 1. Now in this case, I'm just going to do a simple x and y, but I did something wrong here on purpose. What did I do wrong? You can't use y. You can use x and f of x because that's the name of the function. Let's pick some values. -2, -1, 0, 1, and 2. If you plug these in, let's start with -2. -2 squared is 4. 4 plus 1 is 5. -1 squared is 1 plus 1 is 2. And if you continue this on, we would get our other points. So let's graph this. In this example, we're going to graph our points. Negative 2, 5. Negative 1, 2. 0, 1. 1, 2. 2, 5. It looks similar to the last one. But this is an x squared function. Let me just tell you that anytime you have an x squared, this is something called a parabola. And this is going to be like a u. It's going to curve. It does not come to a point, and this is, actually I could draw this better, but it's almost like a u. So it's going to have a rounded, smooth curve at the bottom. And we are now starting to show you how you can graph other things. How you can graph other things just on lines, because lines are not the only functions we have.